Welcome to the video. In our last videos, we have fully discussed the Hyperfoam model in Abaqus software. In this session, we will demonstrate the simulation of indentation of an elastomeric foam specimen with a hemispherical punch using Hyperfoam model. In this example, we consider a cylindrical specimen of an elastomeric foam, indented by a rough, rigid, hemispherical punch. This problem illustrates a typical application of elastomeric foam materials when used in energy absorption devices. This problem can be solved with low computational cost using axisymmetric model. The foam specimen has a radius of 600 mm and a thickness of 300 mm. The punch has a radius of 200 mm. The bottom nodes of the mesh are fixed, while the outer boundary is free to move. The Hyperfoam model is defined using experimental test data. The punch is displaced downward by a prescribed displacement boundary condition in the first step, indenting the foam specimen by a distance of 250 mm. In the second step, the punch is displaced back to its original position. Let's see how to simulate this problem in Abaqus software. Don't forget to like, comment, subscribe and hit that notification bell to get new video updates. First, we create the hemispherical punch part. Select the Create Part icon. Enter the name. Select Axisymmetric. Then, select Analytical Rigid. Now select Continue. Create an arc with the radius of 200 mm. For this purpose, select this icon for creating arc with center and two endpoints. For the center point, enter 0 and 0. For first endpoint, enter -200 and 0. For the second endpoint, select an arbitrary point on the grid. First part is done. As a last step, define a reference point for the punch part. Now, create the foam part. Again, select the Create Part icon. Enter the name. Select Deformable. And now select Continue. Select the Create Rectangle icon. Enter 0 and 0 for the first point. Enter 600 and 300 for the second point. Second part is done. Now we enter the Property module. Select Create Material icon. Enter the name. Now, select Mechanical, Elasticity, Hyperfoam. As we have discussed in our previous videos, we can specify Hyperfoam material properties directly or allow Abaqus to compute them. In this example, we follow the second approach. Therefore, the elastomeric foam material is defined using experimental test data. Therefore, at first, toggle on the Use Test Data option. The order of the series expansion is chosen to be 2, since this fits the test data with sufficient accuracy. For the material used in this example, the effective Poisson's ratio is 0. Select Instantaneous for the moduli time scale for this example. The uniaxial compression and simple shear data stress-strain curves are shown and corresponded data are given in the tables. To enter experimental data, select Sub-options, and then, select the corresponded test. Important note: the test data are defined in terms of nominal stress and nominal strain values. Compressive stress-strain data must be negative. Now, select Create Section for the foam material. Enter the name. Select Solid and Homogeneous. Then click Continue. And finally press OK button. Now assign the section to the foam part. For the orientation assignment. At first, we must create a datum rectangular coordinate system. Now select Assign Material Orientation. Select Datum Coordinate System list. Choose the created coordinate system from the list. Click OK button. Now, enter the assembly module. Import both parts into the assembly module. Then, translate the foam part to right below the hemispherical punch part. Now, enter the step module. Select Create Step icon. Enter the name, which is loading. Select Static, General. Toggle on the nonlinear geometry, since the foam part undergoes large deformation. And adjust the settings of the incrementation section. Similar static, general step must be defined for the second step, which is unloading. For plotting reaction force versus displacement of impactor, history output is required. First, define a set. From Tools, select Set and then click Create. Enter the name. Select the reference point of the hemispherical punch part. Now, select Create History Output. Click Continue. For Domain option, select Set. And then, select Reaction Force and Displacement in the thickness direction. And click OK button. Now, enter the Interaction module. Select Create Interaction Property. Enter the name. From Mechanical section, choose Tangential Behavior. Choose Penalty Formulation. The friction coefficient between the punch and the foam is 0.8. Click OK button. Now, select Create Interaction icon. Enter the name. Choose Surface-to-Surface Contact. Select the punch part as master surface. Select the upper edge of the foam part as slave surface. Everything looks good and click the OK button. Now, enter the Load module. Select Create Boundary Condition icon. Enter the name and choose the step. Select Displacement/Rotation option. Select the bottom surface and set all the degrees of freedom to 0. Similar for the center edge. Enter the name. Set the U1 to 0. Similar for the hemispherical punch part. Enter the name. Select reference point. and set U1 and UR3 to 0. Now, define loading boundary condition for the first step. Enter the name and choose the step. Select reference point. Set U2 equal to -250 mm. As a last step, define unloading boundary condition for the second step. Enter the name and choose the step. Select reference point. Set U2 equal to 0. Don't forget to deactivate the loading boundary condition for the second step. Now, enter the mesh module. The mesh refinement is biased toward the center of the foam specimen where the largest deformation is expected. Select Assign Element Type icon. Toggle off the Reduced Integration option. Now the model is ready to be solved. Create a job and then submit the job. Once the job is completed, click the results. You can observe the stress contour plots or displacement variation in the foam part during the loading and unloading step. For plotting the reaction force versus displacement curve, first select Results from the menu bar. Then select History Output. Find your history output. You can observe their variations over time. Now, save them as absolute value. Select Create XY Data icon. Choose Operate on XY Data option. Now choose Combine Function. And then, add displacement and reaction force data. Now you have the reaction force versus displacement for both loading and unloading. Important note: loading and unloading curves are light on each other, since we didn't consider viscoelastic property of foam. Thanks for watching the video. If you are interested on simulating foam materials using Abaqus software, please like and subscribe and click the bell icon to get new video updates. Don't forget to visit our site for more related products. Have a great time.